So, let me write what I just did. So, let me write it as a theorem. So, theorem, let A and B be two similar matrices, fine. Then A, alpha belongs to sigma A, that alpha is an eigenvalue, alpha is an eigenvalue of A if and only if alpha is an eigenvalue of B, fine. That is one thing. 2 or B part, for each alpha belonging to sigma of A, fine. Algebraic multiplicity of alpha as an eigenvalue of A is same as algebraic multiplicity of alpha as an eigenvalue of B, that is also same. And C, for each alpha belonging to sigma A, geometric multiplicity is also the same. Multiplicity of alpha as an eigenvalue of A has the same geometric multiplicity as B. Is that okay? So, all the three are true. So, whenever I am looking at symmetric transformation, everything is nice, fine, because I am multiplying by invertible matrix, that is more important. So, multiplication by S and S inverse, that is what is all right. So, fine. So, let us again understand it nicely. So, proof, what we did was that we looked at determinant of, so A and B similar, A and B similar implies determinant of implies A is equal to SB S inverse for some non-singular matrix non-singular S or invertible matrix S, whatever you want to say. So, for we need to compute, so for eigenvalue we need to compute determinant of xi minus a. So, eigenvalues, for eigenvalues, roots of the polynomial, all right, characteristic polynomial. So, this which is same as determinant of, we have done it, xi minus a is nothing but SB S inverse, which is same as determinant of, I can write x as it is, replace I by S identity S inverse minus SB S inverse, which is same as determinant of, I can take common here S this side, S inverse this side, I get here xi minus b here, which is same as determinant of S into determinant of xi minus b into determinant of S, which is same as determinant of xi minus b. So, what we are saying here is something more, that characteristic polynomial of A and B are same. Since their characteristic polynomial is the same, and therefore, we get A as well as B both together at a time, because algebraic multiplicity was only related with the characteristic polynomial, the roots of the characteristic polynomial, right. So, this gave us algebraic multiplicity of alpha as an eigenvalue of A was the multiplicity of alpha as a root of the characteristic polynomial, all right, fine. Now, let us look at the geometric multiplicity. How do I prove the geometric multiplicity? So, for geometric multiplicity, geometric multiplicity of alpha as an eigenvalue of A, we need to look at dimension of null space of alpha I minus A. I need to compute this. So, suppose the dimension is k, suppose dimension of this is k, this implies I can choose a basis. So this implies there are k linearly independent vectors in the null space of alpha I minus A. So let u1, u2, uk this be a basis of null space of alpha I minus A. Fine. So this is basis means that alpha I minus A multiplied to ui is 0, which is same thing as saying that. So this is for 1 less than equal to I less than equal to k, I get this, which is same thing as saying that A of ui is equal to, just look at this, A of ui is equal to alpha ui for 1 less than equal to I less than equal to k. Fine. From here I want to go to B. And we have assumed that A is equal to this. So we have assumed, what we have assumed? A is equal to SB S inverse, all right. So let us use this idea. I know about A, I want to go to B now. Fine. So I can rewrite this. So I can rewrite this as, just have a look at it nicely. I can write B as, fine, S inverse AS. I can write like this. Fine. B is, S inverse will go on the left and S will come on the right. Fine. What I know is, I know about A of ui. There, how do I multiply by ui? If I multiply by ui, there will be a problem here. So what I can do is that I can get rid of this S. So get rid of S. If I want to get rid of S, I will have to multiply this by S inverse, all right. So let us look at B times S inverse of ui. So this will be equal to, B is S inverse AS, you are multiplying by S inverse of ui, and therefore what you get is S inverse of, S and S inverse cancels out, A here, SS inverse of ui, which is S inverse of AUI, which is S inverse of AUI is alpha ui, which is same as alpha times S inverse of ui. Fine. So you can see here that I have got here this, that B times S inverse of ui is equal to alpha times S inverse of ui. Fine. So this implies S inverse of u1, S inverse of u2, S inverse of uk, this is a basis of null space of alpha I minus B with a question mark. Why a question mark? Because we do not know, till now we have not shown that this is linearly independent, linear independence. So there is a question of linear independence, all right. So recall that if I had a linearly independent set u1, u2, uk, if I multiply by any invertible matrix, the linear independence is maintained, all right. So here S is an invertible matrix and I am multiplying by S inverse, which is an invertible matrix, to a linearly independent set. So again emphasizing, if you have a linearly independent set, multiply by an invertible matrix, whether on the left or right, whatever it is. If you are able to multiply, if your multiplication makes sense, then you again get a linearly independent set, all right. So therefore this will be a linearly independent set. I cannot say now, so I have got that this is linearly independent set. How do I say it is a basis? All right. So our argument implies S inverse of u1 till S inverse of uk is a subset, LS of this is a subset of null space of alpha I minus b. Can it have more elements? Question. So this, does it span null space? That is the question. All right. So what we know, we have been given. So let me just write it again. So started with, so given what we had given, that this set u1, u2, uk was a basis of null space of alpha I minus b. From there we got that this will imply that this is linearly independent, these are linearly independent, and the linear span is a subset of this. Fine. Question is, can I have more elements in the basis? Fine. So question, can we have more elements in the basis of null space of alpha I minus b? All right. So what we have done, I wrote it wrongly here, it is a here, alpha I minus a here. Fine. So from null space of alpha I minus a, I went to null space of alpha I minus b. This is what I did. So from K I got something. So here what we are saying is that what we have shown is that dimension of null space of alpha I minus b is greater than or equal to K. Fine. So from K I went to say that this is greater than or equal to K. If I start with a T here, the same argument, all right. So if I start with a basis here, say V1, V2, VL, if I start with this here, fine, I can go here and then look at SV1, SV2, SVL. I can go to this. Again, S is invertible, so this will be linearly independent set, and this will imply that dimension of null space of alpha I minus a will be greater than or equal to L. Fine. So from K I have got that this is greater than or equal to K. From this part, all right. So this is T I wrote, so T here, T here, T here. All right. Fine. Fine. So from 1 I can go and say that dimension is greater than or equal to K. I can go the other way around to say that its dimension is more. So the dimension of the 2 is the same. All right. So you have to be careful. You have to understand this. This is very important. Fine. So what we have shown is that if two matrices are similar, then they have the same eigenvalues. Their algebraic multiplicity is the same. Their geometric multiplicity is the same. All right. Fine. What more? So let us look at example which you have already done. I am just trying to recollect for you. Look at this matrix A, which is 0, 0, 0, 0. The matrix B, which is 0, 1, 0, 0. Both of them have the same eigenvalues. Both of them have 0 as eigenvalues of algebraic multiplicity 2. Fine. Both of them 0, 0, 0, 0. Fine. But they have different geometric multiplicity. All right. So recall E1, E2 as my eigenvectors, because A of E1 is 0 times E1, A of E2 is 0 times E2. But in this case, if I look at B times E1 was 0 times E1, and we didn't have any other vector x linearly independent with E1 such that Bx is equal to 0 times x. All right. So understand them, that if you have similarity, everything is nice. If there is no similarity, there is a problem. And again recall, I am telling you again and again that similarity means changing the basis. This is what we had done at the time of defining itself when we looked at linear transformations. I think the last slide or last lecture in that part, that whenever we look at matrix of a linear transform from T of A to T of B, all right, then the notion of similarity comes into play. So, you are just changing the basis and trying to get things. So, whenever I change a basis, properties do not change, everything is nice, fine. So, I would like you to keep track of this part, fine. As the last thing in this lecture, I would like you to understand this theorem, and I want you to understand the argument here, because a similar argument will be used at different place also, fine. So, let A belong to Mn of C and this with alpha belonging to a spectrum of A, then algebraic multiplicity of alpha as an eigenvalue of A is greater than or equal to geometric multiplicity of alpha. Is that okay? Proof. Very important idea. It gives you idea of how do we play around with matrices, eigenvectors, eigenvalues, linear independence, dependence, and so on. How are we playing with things? That is very important. So, understand it nicely. All right. So let geometric multiplicity of alpha as an eigenvalue of B be k. Suppose it is k. What does it mean? It means that dimension of null space of alpha I minus A is k, implies we have eigenvectors. So, whenever we say eigenvectors, they are linearly independent eigenvectors u1, u2, uk, a basis of null space of alpha I minus A, fine. Is that okay? So, what we have is A of u1 is equal to alpha u1, A of u2 is equal to alpha u2, so on till A of uk is equal to alpha uk, fine. I have this, fine. Now, u1 to uk is a linearly independent set, in Cn over C, all right. So, we can extend it to form a basis. So, extend it. So, extend it, all right. So, before extending it, let me first make this. So, first make UIs orthonormal. I do not need it, all right. I need the other part to be orthonormal or orthogonal at least. So, make UIs orthonormal, important. I did not say it directly, but indirectly I said in the very beginning because of linear independence that important, that if u1 and u2 are eigenvectors, then their linear combination is also eigenvector. So, if u1, u2, uk are eigenvectors for the same eigenvalue alpha, then for any choice of scalars C1, C2, Ck, this vector x, which is summation Ci ui I is equal to 1 to k, all right, with x not equal to 0 is also an eigenvector for alpha. Is that okay? That you can check Ax is equal to A of Ci ui, which will be equal to Ci A of ui, which will be equal to Ci alpha ui, which is same as alpha times summation Ci ui. All right. So I can make ui's to be orthonormal. All right, that is the first thing. So what we have shown is that I can make ui's orthonormal. Now 2. So without loss of generality, let ui's be orthonormal. All right. 2. Extend the linearly independent set oblique orthonormal set to get an orthonormal basis of Cn over C as u1, u2, uk plus 1 till un. Is that okay? So I have got this basis now. And now I want to multiply things and see what is happening. So define the matrix P as u1, u2, uk plus 1 till un. Let me write this. Now this is an orthonormal basis. So P inverse is same as P star. Fine. Because I don't know whether the ui's are real numbers or complex numbers. I do not have anything, but I know they are over Cn. So I can talk of unitary matrix. So P is a unitary matrix, because we have taken this as orthonormal. Fine. So let us compute P star AP. Fine. So what is P star AP? P star is P inverse itself. So let me write P star here. And what is AP1? So AP will be equal to A of u1, A of u2, A of uk, A of uk plus 1 till A of un. Fine. So this is equal to P star. Look at AU1. AU1 is nothing but alpha u1. AU2 was alpha u2, alpha times uk. Fine. I do not know what they are, these parts. I don't have any handle on those parts. Fine. But I knew that u1, u2, uk, they were eigenvectors corresponding to alpha. So therefore I will get alpha here. Is that okay? Now when you multiply P star with alpha u1, what do I get? P star, if you look at this, we are saying that since it is a unitary matrix, P star P is identity. Fine. It means that u1 multiplied to P star is nothing but 1 0 0 0. Fine. So look at the matrix multiplication again here, recall. So P star P is identity, means that well multiplied P star with u1 will give me e1, P star with u2 will give me e2, and so on. P star of un will give me en. All right. That's the way we multiply. Fine. Because P star will go inside. So recall here, P star P will give me P star u1 till P star un, and this is my identity. All right. So this is the way it is. So therefore what I will get here is, this will give me alpha 0 0 0, this will give me 0 alpha 0 like this. For alpha k again I will get 0 0 0 and alpha here. So this part will be 0. Fine. I do not know. So let us look at these parts. I do not know what they are. So there will be some things here. Is that okay? So at this stage I only know that I have got a k cross k block of alpha times identity ik. Is that okay? I have got this. Fine. And therefore from there I want to make statements about the whole thing. So what I have seen here is that P star and P, they are invertible matrix, and P star, so this is same as P inverse AP. Fine. Since they are the same, so I am saying that the matrix A and this, they are similar. So the matrices A and P star AP are similar. Fine. Since they are similar, it means that they have the same characteristic polynomial, algebraic multiplicity is the same, geometric multiplicity is the same, and so on. Fine. So, what we know is that they are similar. So, this implies algebraic multiplicity, this implies characteristic polynomials are same. So, this will imply that look at so now look at the characteristic polynomial of P star AP. So, the characteristic polynomial of P star AP will be determinant of xi minus P star AP, which will be equal to determinant of x times 1 0 0 0 1. So, this is 1 here on the main diagonal minus P star AP, P star AP at alpha I k here, something here 0 here and something here. This is what I had. Fine. So, this will give me determinant of, just look at this part also, I can just break up like this. So, I will get here x minus alpha times I k, I will have something here 0 here and something here. Fine. So, this determinant of this part now I can look at is as x minus alpha I k is there is a 0 matrix here. So, determinant of this will be determinant of this part into determinant of this part. So, if I write this as b, then I will get it as x minus alpha to the power k into determinant of b. Is that okay? Fine. So, therefore, from here we see that this implies algebraic multiplicity of alpha as A, which will be same as algebraic multiplicity of alpha for P star AP, which is greater than or equal to k, because as determinant of B is also a polynomial in X of degree n minus k and may have alpha as a root. All right. I am not sure whether what is B. I do not understand, I cannot understand what the B is, what are the entries of the B, but at least I know that since geometric multiplicity, so since geometric multiplicity of alpha of A was this number was k, I could get u1, u2, uk which were orthonormal, fine, and then extend it to get the whole basis. I could do that, and therefore, I could get this matrix, and because of this matrix I could say that I have x minus alpha to the power k coming into play, and therefore, I could show that algebraic multiplicity is greater than or equal to k, but what was k? K was nothing but the geometric multiplicity of alpha. This, all right. So, we have shown that algebraic multiplicity is greater than or equal to geometric multiplicity. All right. So, that is all for now. Thank you.